don't know. Does it work? Does it run?
No, we also don't have the MATLAB. Oh, you said if we wanted to.
You should be able to do
copy the MATLAB.
in MATLAB. Yeah, so I can.
That's good.
Oh,
Okay,
yeah,
so
so
I'll use that. I will use that.
there are two ways to do this. Yeah, so the two ways to do this through the notebook, or if you just I was going to put these up and then I realized I was dangerously low on battery, and then I realized I had a thing. So I didn't actually do it during, but you have a version of MATLAB. You can essentially copy paste most of the stuff from here into here. The only thing you've got to be careful of is where it defines functions. So here you define functions in MATLAB in a separate file. There's a way of doing that in Jupyter, so it's not, you don't have to do that explicitly. But if you're just copy pasting code, don't worry about copy pasting this. So long as you're in the right directory and you've got all the stuff up of GitHub, you should these functions should exist and it should just run. So just wherever it's got a double percent and then file, it's creating a function. Wherever it's creating a function, just skip copy pasting that into the MATLAB if you're running it directly in MATLAB. And it should just work. So before I get into the notebook, I just want to just do a couple of slides because it's actually quite nice. It was unplanned, but it's kind of nice how this worked out. So I just set up, especially in that first example, right? So it's a really old school RL algorithms of things like Q-learning and all sorts of temporal difference learning, all sorts of fun things. And these things were developed in the sort of 80s and 90s as sort of machine learning tools. And then I guess it was the 2000s, probably people like Nathaniel Dorr started saying, well, these aren't just algorithms for machine learning. These are actually hypotheses for how people might be learning and how people might respond. And so you can actually start to think about this not as a useful tool, but actually as a model that makes time point by time point predictions, very specific predictions on a trial by trial basis about what people are going to do based on what they've experienced in the recent past. And so there's this big excitement starting in the early 2000s and going on, that you can actually start to make a direct connection between what these algorithms are doing and what people are doing. And the way to do that... Oh, did I turn this off? Oh no, I took it off, sorry. You can make a direct connection between what people are doing and what these algorithms are doing, and actually fit these parameter values, so fit things like alpha, fit things like gamma, and make some inference about how people are learning in these kinds of tasks. And what I want to talk about is just have and what's in these little notebooks is a couple of very simple examples where we work through simulating some task, but then go through some of the checks of how you might fit behavior and extract parameters from behavior, and the sort of it's the boring stuff, right? It's the quality controls to make sure that you're actually saying something meaningful. So I'm going to summarize some stuff that's in this preprint paper that's been sort of doing the rounds. It's 10 simple rules for computational modeling of behavioral data. And what we're going to do in the notebooks, just work through a couple of the examples from that. So we're going to focus on a much simpler task than even the taxi driving task. It's I don't know if it's the simplest, but extremely simple reinforcement learning task. You've got two slot machines. They both pay out with a fixed probability. The probabilities can be different. They don't have to be. You've got to guess or estimate or learn the reward probability associated with each one, and then you've got to use that to make the most money that you can. And a very simple model of this, maybe the simplest model, and this is the model, one of the models we're going to talk about in the notebook. Model 3 is this Rescorla-Wagner learning rule. And this has one state and two actions. It's sort of version of Q-learning. It is actually a version of Q-learning where there's no state, no next state after you've made your action. And you learn a value for each option. You learn this value using essentially a version of this, right, where you've got the Q for option k on time t plus 1 is q for option k on time t plus some prediction error times the learning rate parameter, number between 0 and 1. Alpha, the learning rate, is one free parameter of this model, right? That's ultimately what we're going to tweak to see if we can extract that from human behavior. And then, of course, you also need an update rule for the unplayed option, where we just assume that that new value stays the same, so it doesn't change. And then, okay, so this gets us the learning, but it doesn't get us, we still need one more step to connect to behavior, and that's we need some model of how these values get turned into choices. And the standard, pretty much the standard model that people use in these kind of paradigms is what's called the softmax rule, where I basically just say the probability of choosing option A is going to be some sigmoid function of the difference between the two values. And this gives you something that looks, you know, kind of nice like this, a nice sort of soft max. So pure max would be a hard threshold, pure random would be totally flat, and then soft max is somewhere in between, and the beta parameter, softmax temperature people call it, that beta parameter determines the slope of that thing. The higher it is, the steeper the slope. So with this, we can simulate some values over time, right? We can also simulate some choices from that, but then we can also fit that model to human choices, extract an alpha and beta, and that's really nice, right? And that, in some ways, has been used, or is being used, or is being proposed as maybe these parameters are interested in individual differences, right? So some people have a high learning rate, some people have a low learning rate. Maybe that means something about, I don't know, psychiatric disorders, right? But before you can say that, and this is really the main point of that paper we wrote, is you need to check some things first. So do these numbers actually mean anything? And one thing that you should check and can check very easily, and you'll check in these notebooks, is the minimal condition that if I generate behavior according to this model with known parameters, right, alpha sim and beta sim, and then I take that data that was simulated from known parameters with a known model, I should be able to throw those choices into my fitting, and I should be able to recover the parameters, those same parameters, right? So it should be that the fit, that when I simulate data with alpha sim and beta sim, and I fit that data, just the choice behavior, I should be able to re-extract alpha fit and beta fit, right? That's a minimal condition, and it absolutely doesn't occur all the time, right? Well, very much not. People don't tend to check it in the literature, but also it's not guaranteed to be the case, right? And this is the absolute minimum condition that you need to say anything meaningful about these parameters, right? So what you do to test this is, and what you'll do in the notebook number 2 is just simulate a bunch of data with random parameter values, fit at a bunch, see what parameters you recover, and then plot one against the other. So a good parameter recovery looks like this. Here's the simulated alpha versus the fit alpha, and they all lie on the equality line, right? Here's the simulated beta versus the fit beta on a log scale, because beta, it's just better to represent it on that. And you get a nice parameter recovery. They're all on the line of equality, right? This is what you want. If they're not on this line of equality, that's actually a sign, well, either you've got a bug in your code, which is often the case, or your experiment isn't good enough to distinguish, to extract these parameters. The data you're getting contains very little information about the parameters. Yeah?
Do you have any, I always struggle with what correlation is a good correlation?
Yeah.
Good enough?
I worry with that. I don't have an absolute number on that. Ideally, what you want is something that looks like this. And I think a lot depends on what do you want to do with it, right? If you want to say two groups have different learning rates, you could do things like a simulation of that and say, okay, how well can I distinguish those two learning rates in simulation, even if they are different? So sort of like a power analysis, but filtered through the model. But yeah, there's really no hard and fast rule for that. Ideally,
some correlation like this. I think the real one you want to avoid is, when it's completely all over the place. That's the big one. The other thing you can do with these models is you can compare them against other models and say, which model best describes this person's behavior. So I can have this model, which is Rescorla-Wagner. I could have model 1, which is totally random responding, right? That happens a lot in psychology experiments. I could have another one, which is win, stay, lose, shift, which shares properties with Rescorla-Wagner, but not all of them. And we could ask which strategy best accounts for people's data, right? And this is really actually quite easy to do. You can just look at which is best predicting the data. There are standardized ways to do that. You'll do that in this notebook. But again, you've got to check, are you actually able to distinguish the models from each other given the data that you get from your experiment? And the way you do that is, again, with simulated data. You want to say, if I simulate data with model A and I fit it with all the models, the model that fits best should be model A, at least most of the time, right? If I can't do that, then again, my experiment is not very good. And so here's an example of that, an example that, you're going to make something similar to this, where I've got a bunch of models. Here I've got 5 models. I'm going to simulate all 5 of them. I'm going to fit each of those simulated data sets to all 5 of them. Do it, 100 times, however many times you want to do. And then I'm just going to keep track of how many times does data from model 1 get best fit by model 1, what fraction of the times. And I get this thing called a confusion matrix. And again, what you want is this to be perfectly diagonal. But what you can see here is model 5, it's kind of hard. It's kind of hard to know what to make of this, right? Yes, it's best fit. Most often, the mode of that is best fit by model 5, but it's often fit by model 1 and all the other models as well. So it's hard to distinguish model 5 from other models. So this is saying that there's something wrong with the experiment here. Maybe we need a better experiment. And by a better experiment, that could just be more trials, right? And you can play around with that in the data and in the notebooks as well.
What parameter distributions should we use when you're looking at model recoverability?
So,
Actual ones or the purpose of them?
yeah, so it's a tricky problem. It's a tricky problem. So it's a tricky problem. So yes, you should look, that should be a guide, is that the model parameters that the subjects are in, that's a useful range. But it can be, there's a little, and that's definitely the case for parameter recovery. That's definitely, you want to be able to recover parameters in the range that you think is actually present in your data, right? And you can almost see that in those previous plots where, for beta, right, you can see that the very high betas it's not doing a great job, right? Whereas for the lower betas it is. And so you want to know, does that matter or does it not? For model comparison, it gets kind of funky because then if you're fitting your models to the behavior, you may be in a parameter regime where one model looks very much like another model, right? So say you've got, epsilon greedy choices or something, and epsilon is very close to 0. Well, that looks like just a greedy model, and it may be that you start to confuse those greedy models. So it's a little bit more of a funky thing there. But ideally, you want parameters to be roughly in the regime that you are considering, and also they should be in a regime where the models are truly different. If the models are, actually identical under almost all circumstances for the sort of parameters that you're using, then it's almost as though they're not actually different models. Yeah, great question. Okay, so just switching back over to these notebooks. So there's 3. They're very simple. We're just going to simulate the multi-armed bandit test. There's a bunch of text that I just copied and pasted from the paper just to put it in context. But basically, we're just going to simulate this behavior. I've set the mean of each one, the mean payout of each bandit to either be 20% or 80%. Let's see if that runs. Okay, that's all running. I can My first model is super simple. I make a simulation function that takes in mu. It's just this biased responder. Takes in b. It's got a probability b of choosing right, probability 1 minus b of choosing left. I just loop over all time, got my choice probabilities, choose according to those choice probabilities. This is just a little function that I made to make that a little easier. Generate some reward based on the choice, and then loop through. This is a very boring function, right? But I can simulate it, and if I simulate it and plot it, I can plot the output here. So what's plotted here is the choice. The gray lines and dots are the choice of the algorithm, and then the red dots are the reward, right? Whether it's rewarded or not. Rewarded is red. And what you can see, yes, it's rewarded more when it chooses 2, but the behavior of this model is, stare at this enough, has no, the reward has no relationship with the behavior of the model. You can do the same thing for noisy win, stay, lose, shift, right? This is a pretty simple one. You just have to keep track of what did I do on the last trial and what did I get on the last trial, and then depending on what I got and what I did, if I won, I stay, and if I didn't win, then I switch. And I have this epsilon probability that I'm just going to choose randomly, so it's a sort of epsilon greedy version, if you like, of win, stay, lose, shift. Again, I can simulate data from this, simulate a bunch of choices, and for a low enough epsilon, you can see that lose, it shifts, lose, it shifts, a bunch of losses, it keeps shifting till it wins, and then it stays, and so on and so on. So you can see this has got some connection to the data, or to the rewards. Then I can do, here's my Rescorla-Wagner model. I've got one line in that's just doing exactly what IDA told us not to do, which is store the Q values, right, just so we can plot them later. But I'm computing my choice probabilities basically as this softmax. I've written in a slightly different algebraic form to the one I showed you, but it's the same thing. You can play around with that if you want. I am making a choice according to those choice probabilities, generating my reward, and then crucially I update my values. I get my prediction error is reward minus the predicted reward, and then I update my chosen action value based on that prediction error, right? Basically the same thing as this equation, but there's no new state, so this term just goes away. Okay, so that's nice. Then, we can start to, well, with this one, we can actually plot the values, right? So we've got the values over time. Here's the true value of the high value one. Here's the true value of the low value one. It gets close to the high value one. It reduces its value for the low value one, but it's getting there pretty slowly because at a certain point it stops choosing that option, right? When the values get too different, it's going to stop choosing that option. And there you've got this exploration exploitation problem that the beta parameter can resolve. 2 more models just to flesh it out. This model is always a good model to have in there, or a good component to have in there, this idea of a choice kernel. And this is trying to just pick up the idea that if I do something on this trial, maybe I'm likely to do it again on the next trial just because I like repeating my actions, right? Or maybe I like alternating, in which case I have a negative choice kernel, right? And we can include this as a factor by just saying, by effectively just having a choice kernel which updates a lot like the Q value, but instead of using rewards, it's using the action, right? So if I tend to have lots of ones, then I have a high choice kernel for option 1. I have lots of option 2, I have a high choice kernel for option 2. So I can run through that, create some model, simulate this thing, and get some choices. And you can kind of see this is a model that flips around initially, but then as it builds up, as it chooses option 1 more and more and more, it builds up more of a choice kernel for option 1 until eventually it sort of gets stuck choosing option 1 forever, right? Which is the bad option. There's no reward. Because this algorithm is not sensitive to reward at all, it can randomly just settle on one option randomly. Does that make sense? Last thing you can do, model 5, the most complex model, is you just mix. You mix Rescorla-Wagner with choice kernel. So now your choice probabilities are going to be based on a mixture of the Q values and the choice kernel, right? And so, and they each have a different relative weight, right? So the stronger you weight reward, the more reward sensitive you are. The stronger you weight choice kernel, the more sensitive you are just to keep repeating actions. And again, it's a very simple, they're, very simple algorithms to actually code. You're just going through each one. Contribute choice probabilities as being related to your sum of Q values and choice kernel. Update your values, update your choice kernel, and loop forever. Make sense? So hopefully this is a very simple thing just to stimulate a bunch of these things. And then for this, you can get a choice. This one, in this case, did a great job. You can simulate the values, and you can simulate the choice kernel. Right, so this is fun. You can do all the simulations, but then where it really starts to get fun is when you start to do the model fitting. So what we're going to do, I won't go into all the details of model fitting, but the basic idea with model fitting is I'm going to take my data, right, which is a bunch of choices and the reward outcomes that I saw. Right, so I'm just going to lump this as this D term, all the data from trial 1 to trial T. And I'm going to try and find the parameter values, and I'm going to use theta m for the parameter values of model M. I'm going to try and find the parameter values that maximize the probability that I would see the choices that I actually saw. Right, so this is the probability of seeing data D given parameters theta m and model M, right? I can break this out, this D term, just by not even Bayes rule. It's just probability rules to say that this log likelihood is going to be the probability of making each choice given the data up to that time, and I don't know why there's an ST there, and the parameters of the model. So in practice, what that means is all I need to do is be able to write down a function that computes the log likelihood for a set of choices that I made for each model. And the simple way to do that, or one way, well, this is the way to do that for this Rescorla-Wagner model, this model 3. And it looks very, very similar to the simulation code. So all I have to do is I take in as an input A and R, which are the actual actions and rewards that I saw. I take in the parameters alpha and beta, which are the learning rate and softmax temperature, which I'm going to try and fit, right? So I have to take in a specific value of those. And what I'm going to spit out at the bottom is the log likelihood, actually the negative log likelihood, so that I can use MATLAB's built-in minimizer. They don't have a built-in maximizer. What I do is I go through each trial, in my experience, compute the choice probabilities given my current values of Q, and then instead of actually making a choice, so in simulation I would have made a choice at this line. On this, when I'm fitting, all I need to do is compute the choice probability on this line for the action that I actually saw on this trial. Does that make sense? So I take that choice probability, and then I still update the values exactly the same as I did in the simulation code. Right? So to build a likelihood function, I'm almost taking the exact same code that I had for my simulation code. I'm basically just swapping out the choose line, right, where I actually made a choice on the basis of the probabilities, to the choices already given to me. I'm going to compute the probability that this model would have made that choice if it had seen this past history of rewards and choices. And yeah, and then I'm updating things. And the only other thing that's missing, that's different from the simulation, is that I'm not sampling the reward. I'm actually observing the reward, because I have the history of choices and rewards in there. And then so that's the probability for every trial. I take the sum of the log of those choice probabilities and I get the log likelihood. Does that make sense? I'm going a little fast, but hopefully it makes sense. So I can just run that. Oh, yes.
It's not a question, more of a comment. I've found it sometimes easy to think about this basically in the first case during the simulation, like this, the model is making its own choices basically.
Yes.
And here you take the choices of the participant, for example, but the updating of the values is done by the model, but based on the actual choice of the participant.
Exactly. That's exactly right. So the sort of addendum to that, the follow-up to that is that you can fit any model to behavior, right? So a model that can't do the task, you can still fit that to subject's behavior. And sometimes you can actually find, if you're doing it badly, and I have a real-world example of this, that you can fit a model that cannot do the task in simulation and find that it's the best fitting model of your data. And what that means is there's something missing from your model set. You're missing the actual best model. And actually, it's these choice kernel models that can really do that. So if the minute you have these kind of grid worlds, one of the classic behaviors in these grid worlds is that people will, they'll go in a line like this. They'll explore over here, then they'll explore over here. They won't respond randomly like that taxi cab, right? And so a choice kernel actually will fit that data very well in fitting, because what does choice kernel says? It says you tend to repeat your past action. So you get from choice kernel these long extended lines of movement, right? But they're long extended lines of movement in completely random directions that have nothing to do with the structure of the task. So there was actually an example, not that I was directly involved in, but it caused a lot of debate, where we had something like that, where the best fitting model was one that in simulation could categorically never do the task. And obviously, people were doing the task, so it wasn't the right model. So that was one of the moments when I realized 10 years later, I had to write this paper. But yeah, so there's tricky things there. Okay, so this is just bringing back that simulation code to compare. So again, the simulation has the choose and it has the sampling rewards, whereas the fit function just has the compute the probability of the known option. Okay, so now we can just start to fit this thing. So I can simulate a bunch of trials from the Rescorla-Wagner model for a particular value of mu, and I can evaluate the negative log likelihood of those choices for different parameter values, beta alpha hat and beta hat. And I get some number out, which is just some negative log likelihood. And what I need to do is basically just play around with alpha hat and beta hat to find the minimum point. So before we do the sort of clever ways of minimization, it's always good to do the dumb ways of minimization. So one thing you can do is just say, okay, let's fix beta, and I'm going to assume I know beta. And let's just vary alpha between 0 and 1. And let's see what that negative log likelihood looks like. And so if you plot it, you find there's a minimum for this negative log likelihood, and this would be the best fitting parameter for this value of beta. And I think I put in a simulation 0.1, and it's giving me out 0.2. So it's not terrible, right? But it's also not amazing. And the way I've set up this example, hopefully, is that it's actually not amazing. And the reason it's not amazing is because I'm only getting 50 trials in my simulation, right? And we can play with that, or you can play with that. Okay. So that does it for one. That's like the stupid way of doing it for one simulation, right? To do this direct visualization. What I want to do now is do it for a bunch. Do it for one, but do it in a smart way. So do the minimization in a smart way. And in the MATLAB world, the way you do the minimization in a smart way is with this fmin_con function that just means function minimization with constraints, right? And what that does is it takes in an objective function, so the negative log likelihood function, and it will minimize it. So the way I pass a function in MATLAB speak is I use these function handles. That allows me to pass a function as a variable. I define, this is going to do some kind of gradient descent on this, some kind of clever search of that space. I need to define an initial point in parameter space to start from. Well, I'm going to do that randomly. I'm going to say the learning rate is just a random number from 0 to 1, and the beta parameter is just simulated from this, sampled from this exponential distribution. I need a bunch of empty things, which can capture, all of these empty things can capture different kinds of constraints, linear constraints or equality constraints on the parameters. So it could be that parameter 1 can never be bigger than parameter 2, right? There are some cases, such as a DDM model, you can never have the starting point be higher than the threshold in a DDM. We don't need to worry about that for this because there's no constraints between alpha and beta. We do need, though, a lower bound and an upper bound. So our lower bounds for both of these are 0. Our lower bound for alpha is 1, and our upper bound for alpha is 1, and upper bound for beta is infinity. So I put these things in, and it's going to spit out the fit values of x and the negative log likelihood at the best fitting value of x. And when I do that, I find my best fitting values are 0.23 for the learning rate and 4.5 for beta. Does that make sense? There's, you know, it's one of these ones where it's really just like a recipe for doing this thing. And for the longest time, I could never remember this. It probably took me 5 or 6 years to implicitly learn the functional form of fmin_con. I would just copy and paste from, I think, YAL's code and just adapt it accordingly. But it really is just, you know, this 5 lines. Define the objective function, initial point, lower bound, upper bound, and then call fmin_con. It really is just this little recipe for doing it, and once you have it, you can do it for anything, right? So it's almost the same thing for anything. The only thing that will change is if you have more parameters in your model, you'll have more parameters. These vectors for initial condition, lower bound and upper bound will be longer.
Just a practical question. So for the parameters, you replace them by this x.
Right. Oh, sorry. Yes.
X2, and then if you would have more, you would have like x3. Yeah.
Exactly. So just the way I'm defining this function handle, I say this at x. That tells me which variables in the upcoming function are going to be the inputs to the objective function. I have this likelihood function. That's the function that I want. I give it a and r. So I've already defined a and r, the choices and the rewards, right? And so those go into the sort of implicit now in the function handle. And then I have the initial, I have the x1. That's the, if you look at the definition of this, that's the position that alpha is. And x2, that's the position that beta is in that function call. Yeah.
And another quick question. I guess you could also code this in a way that you have a kind of more generalized function for the log likelihood, and then just pass in like a model basically, and then you can have all your different models just pass them through the same log likelihood function that is then like minimized.
In the sense you would almost have a function handle for the
Right.
for the simulate. Yeah, there are sort of cleverer ways of doing this that take advantage of repetitions in the code because they all have the same environment, right? So you could definitely make smarter versions of it. When we were making these examples for the paper, we were quite explicit. We wanted it to be simple, so that it's the first pass. The first time you do this, it's often easier to think of the environment and the agent in the same script, even though more generally that's not a good thing to do.
Just a practical comment. Don't use this to optimize a neural network with 5 parameters because it'll never end.
Right.
So there is a speed constraint to fmin_con, although it's
Yeah.
really great.
That's right. So yeah, so these parameters, this parameter search is going to be, you know, it's good for some things, it's bad for others, but in general, the more parameters you put in your model, the slower this is going to get. So definitely If you've got a neural network model with 1 million parameters, forget it, right? You can fit 5 with this. It just takes a while. It takes. Okay. I guess it depends on the size of the space as well, and the gradient. So there's all sorts of annoying things that fmin_con spits out at you to say whether it's converged or not converged. All sorts of bugs fmin_con will pick up on in your likelihood function code, because it's going to be taking your code to weird parts of parameter space to try and find the best fitting parameters. So if you've got any kind of bugs anywhere where choice probabilities go to 0, and so the log likelihoods go to infinities, that can be a bad part of your space. So there's all sorts of like just practical problems with this that is just par for the course, I'm afraid. Okay, so now we can get to parameter recovery, right? So now we can simulate data and we can fit data. So we just do it repeatedly, right? So hang on, where am I? Yeah. So I am. What am I doing here? Yes, I'm making a function that will fit the Rescorla-Wagner model, just so that I can do that in a single line. So then I'm just going to go through, do it 100 times. I'm going to have random alpha and random beta, so different alpha and beta each time, right? That's important if you want to know how you recover over a range. Already answered to, said in response to Kate's question, these parameters should be in a range that you think is likely. God, don't kill your computer. fmin_con didn't converge, god damn it. So then I'm simulating the data. I'm going to fit the parameters using this fit function, and then I'm just going to pull out, keep track of the simulated parameters and the fit parameters on every trial, and then plot them as a scatter plot. And the whole idea here is that it does really poorly. So I showed you an example where it does really well. This is an example where it does really poorly. And the reason it does really poorly, well, is the number of trials. So if you repeat this example with 1,000 trials instead of 50 trials, you will find that this plot changes a lot, and it becomes much cleaner, right? But this is the kind of thing that you need, because you might not know this, right? If you just fit your parameters and pull out some parameters from a 50-trial experiment, there are experiments that have 50 trials, right? Especially when we talk about fMRI experiments. If you want to make strong claims about learning rate in this paradigm, that's a dangerous place to be going, right? Maybe you can say something if there's a group that's really low and a group that's really high. The correlation is not 0 here, right? But it's really, you've got to be really careful about saying something. Does better for beta. It's kind of interesting. But again, these high betas, it does really poorly. And some of the low betas, it does pretty badly as well. So there's, sort of a cautionary tale. And I think this is the real, if you take nothing else from this tutorial, it's that if you are going to use a model-based analysis to connect data to some model and make some story about the model and best fitting models or best fitting parameters, you really want to show that you can do your analysis with simulated data in a meaningful way. Because if you can't, and you often can't with just the baseline things, remember this is a model with 2 parameters. There's not a lot going on in this model, and it's already got all these problems in this very simple task. When you're going up to 5, 6, 7 parameters, you've got to be really careful you're not, saying something foolish. Okay, last one is just model comparison. So we can do the exact same thing, right? That was just simulating and fitting one model. Now I'm just going to simulate and fit 1 million models, and I'm going to compare them to see which one fits best. And I'm going to use this Bayes information criterion score. Probably familiar with it. Basically, I want the model that has the best log likelihood, right, that predicts the data the best, but I want to penalize models that have lots of parameters. That's what this KM is, in some way, right? Because if I don't penalize models that have lots of parameters, well, the best model is a model with the same number of parameters as you have trials, where every trial is just a different parameter, right? That's not a model. That's not an interesting model, but it would fit perfectly. And so the way you beat that is by having this penalty for free parameters. There are other ways of comparing models. There's the AIC. There's other ways you can do if you do these Bayesian hierarchical type model fits. All of what I'm going to say still applies. You can still check whether your way of comparing models makes sense in that it allows you to separate and identify models. Yeah.
Use like model comparison like in the simulation to figure out what metric to use. So for example, like it looks like
Yeah.
here that your model, like model 5, I think had the most parameters and it was recovering poorly.
Yeah.
Does that mean you should be like, oh, I should switch to AIC because
Certainly, it would be a principled way of saying, of distinguishing between them. In practice, people often report both, right? But certainly, it would be a principled way of, if you know, you have, reason to want to choose one over the other, this might give you reason to choose one over the other.
if like for example AIC and BIC are leading to like different conclusions, does that mean like you just don't really know anything?
Well, so the question comes here because you have ground truth, right? If I've simulated data, then I know what the model is, and so they can't give me different answers and both have a diagonal confusion matrix. And so one should have a more diagonal confusion matrix than the other. I think if you are in a regime where it's vastly different behavior in terms of your real data for AIC, BIC, you do want to be really careful. And I think these kinds of things can do it, but it could be that neither does well. I mean, I think you can certainly have neither does well, and they do well in different ways. So this, so now I just have another function which fits them all, and there's these sub-functions which are all on the Git that fit the M1, M2, M3, M4, M5. And so this is going to take the simulated data in, fit all the models, and then spit out some identity of the best fitting model for this set of data, and also all the BIC scores. So I can generate some data from model 3, right? Again, using only 50 trials, simulate some data. I can fit all the parameters. It spits out a vector of BIC scores. I want the one that's lowest. The one that's lowest is model 3. That's good because model 3 actually generated this data. Tells me I best is 3, and then it gives me one of these one hot things, right, with a 0 everywhere and 1 at model 3. Then the last little trick, I can do this many times for all models. So this one can be a little slow, so I'd keep n repeats relatively low, unless you want this to be running a long time. In general, when you report it, you want to do it maybe 100 times per model. I'm going to simulate a bunch of model 3. I'm going to fit that, and I'm going to say how often does data generated by model 3 get best fit by model 3? And actually, it's really bad. Most of the time, it gets fit by model 1, right? And that's because I've only got 50 trials. It's quite hard to distinguish between these behaviors when you've only got 50 trials. This is also a bad experiment because my means are fixed over time, right? So you could imagine in this situation, after 10 trials, I've figured out option 2 is better, and I just always choose option 2. And that is very, that could be a very, very hard to tell the difference between that and a choice kernel, or that and a choice kernel plus Rich-Scholar-Wagner, or that and win-stay-lose shift. Yeah.
When are you using the AIC and BIC criteria instead of just cross-validating your log likelihood?
So you could do that as well, right? You could do that that's a different way of doing it. I think there's some tricks when it's sequentially dependent, right? So you can't just sort of break your data and say, I'm going to split off random trials and train on one half and test on the other. There are some subtleties there that in these sort of sequential dependence, but you can do it. You can do it. You can totally do it. You could, the important thing is you can still do this analysis right, you can still do this analysis with any kind of model comparison metric, right? So you can still do it with cross-validation, and you can ask, how often does model 3 get best fit by model 3 under this one, right? And that is more principled in some sense, right? But you know, it's not guaranteed to be. I mean, the experiment can just be terrible. It could be that you can just not distinguish between these models with this experiment. You know, modeling doesn't get you around that, and that would come out in the analysis, in this analysis as being a confusion matrix where maybe model 1 is always best fit, regardless of what simulated the data. So, yeah, so you can absolutely do all kinds of ways to compare models. What this does is validate that when you do that on simulated data, which is the best case scenario, you can still get out what you put in. Does that make sense? So yeah, good question. Okay, so here I'm just adding more trials to make it 1,000 trials, and now I can recover model 3 10 times out of 10. The very last point is just to do this a bunch of different times for all the models, right? So now 10 repeats, I'm going to do model 1, fit it with all models. I'm going to do model 2, fit it with all models. Model 3, fit it with all models. And now I can create the confusion matrix that we've already seen. And when I do that, I get this confusion matrix, which is great at separating models 1 and 2, but starts to do very poorly at the later models. And if I up the number of trials, this will become much more diagonal. If I up the number of trials to like 10,000 or 100,000, it will do even better. Does that make sense? So, I mean, there's more to, you know, lots you can play around with this. But the main point I really want to take, or you to take from this, is that if you're doing these crazy model-based analyses, they are really powerful. That you can pull out, you know, parameter values that, you know, are really nice, and maybe they even give you insight into mechanism. But oftentimes, the experiment is not good enough to do what you want it to. And you need to check. And as much as anything else, it also checks for bugs in the code, because that's the other way that this thing doesn't work. If you've got the wrong minus sign in the BIC, that can also cause weird things like this. Yeah, so that's, I mean, I'll let you play around with the Python notebooks, but that's basically it.